So welcome everybody to this afternoon session of analysis of seismic, hydroacoustic and infrasonic monitoring data. I have the honor to co-chair this session with Paul Richards, whom I'm sure you all know. Just a few things to mention in the beginning. I would like to ask all the speakers to keep the time. That's 12 minutes presentation and another 3 minutes for questions. So if you go over the 12 minutes, then this will be taken from the questions. Also, let me remind you that there is a poster session with the same topic, theme, on Thursday. The lightning session is at 9 a.m., then the poster session will be from 10 to 11. And then there is a virtual session, e-poster session on Thursday as well at 6:30. So with that, I think we can start with the presentations. The first presentation is by Tibi, and it is testing the design of discriminants for local seismic events recorded during the Redmond salt mine monitoring experiment in Utah. You can control the slides, but there is no point. So this is. This is forward.
My name is Rigobert. I'm from Sandia National Lab. I'll be talking about presenting the result of the work we did with my coworker, trying to discriminate event recorded during the Redmond mine experiment in central Utah. I will start by acknowledging my coworker, Nathan Downey, who is also from Sandia National Lab, and Ronald Brogan from ENSCO. Next slide, please. I think that's, yeah. Okay, the Redmond mine experiment in Utah was designed to record seismoacoustic data at distances less than 50 kilometers. Mostly for algorithm testing and development. And during the experiment that ran from October 2017 to July 2019, we deployed 6 broadband stations. And for 3 of the stations, the location was fixed. For 3 other stations, we moved the location around every 1.5 to 2.5 months. And the Redmond mine operation consists of nighttime underground blasting, and this occurs several times per week. The map on the left shows the location of the stations, and the red box is the location of the mine. On the right, I'm showing you the operational timeline of the station, color-coded as shown in the symbol you see in the map. From about November 30 to the end of the experiment, the station configuration did not change. Next slide, please. And using data recorded during the experiment, we were able to build about more than 1,000 events. And from a subset of it, from a subset of the event, about 280, both the local magnitude and the quarter duration magnitude are well constrained. And based on the location of the event and the onset character of their signal, this subset of events were divided into 3 categories. The Redmond mine event, tectonic earthquakes, and tree blasts associated with a mine located 8 kilometers from the Redmond mine. On the right, I'm showing you the map with the location of the event. You have the earthquakes in red, and the mining blast in navy for the Redmond mine event, and green for the event associated with the mine that's 8 kilometers from the Redmond mine. The size of the symbol are proportional to the magnitude of the event. For the 3 events shown in green, they are co-located. So you see only one circle there, but there are 3 events at that location. Next slide, please. So on the left top, I'm showing you the distribution of the local magnitude for the events for which we were able to estimate the magnitude. And on the bottom plot, I'm showing you the distribution of the Coda duration magnitude. And the gray bar in those plots indicate the event for which we were not able to estimate the magnitude. In the middle plot, I'm showing you the Coda duration versus the Coda duration magnitude versus the local magnitude. You can see that the dashed line in that plot is the one-to-one line, the line of equal value. You can see that the earthquakes follow more or less the one-to-one line, but the mining blasts significantly off that line. And we think that this is due to the fact that you have a enhanced coda for those events because they are shallow. A phenomenology that Copper described in his 2016 paper. So we had enhanced coda that increased the magnitude of the event relative to the local, the coda magnitude of the event relative to the local magnitude. On the right in the slide, I'm showing you the distribution of ML minus MC, red for the earthquakes and navy for the Redmond mine event. In the bottom plot, I'm showing you the median value for those difference in magnitude, and also the associated absolute median absolute deviation. We perform a statistical test for the distribution, and the test suggests that those the event population are statistically distant. Next slide, please. So here I'm showing you for each of the event category example seismogram. On the top in red, you have the earthquake, which is characterized by large S wave. That's to expect. That's what we expect because it's a shared dislocation mechanism. And for the mining blast, you have there's no S wave, but you have a strong RG wave, will indicate that those events are shallow. For the earthquake, we saw no RG wave because they are probably too deep to excite RG wave. In the right plot, I'm showing you the spectra for each of the seismogram shown on the left for the segment indicated with the horizontal bar in figure A. For the smaller event, we were able to upscale. We had to upscale the spectral amplitude so that the average amplitude for the plateau are the same among the three events. So you can see that if you compare the event in red, which is the earthquake, and the event in green particularly, which is the mining blast related to the mine about 8 kilometers from the Redmond mine, you see that you have a steeper fall-off slope for the earthquakes, indicating a relative deficiency in high frequency energy. So we use those dissimilarity to try to come up with a discriminant that will be able to separate the events categories. Next slide, please. So here, the first thing we did, we exploit the deficiency in frequency, the difference in frequency content by using SG amplitude. Here I'm showing you an example of waveform for the earthquake on the left and the Redmond mine event on the right. And I'm showing you the green bar in the plot indicate the window we use to calculate the root square amplitude. We estimated the root square amplitude for 4 frequency bands, 5 to 10, 10 to 15, 15 to 20, and 20 to 30 hertz. Something I would like to mention here is that we are calculating root square amplitude in time domain. But according to Parsifal theorem, the root square in frequency domain or time domain is equivalent to the root square in the frequency domain. The reason I'm mentioning it here is that I'm going to use that to try to separate the different components that make up the measure amplitude. Next slide, please. So we had a measure amplitude, which consists of a combination of a extension term, side term, and a propagation term. So we need to find out a way to isolate the source term to investigate the classifier. And one way, I mean, the best way we thought we could do that is by using the approach described, that was first proposed by Yards in 1993 and is described in detail by Kidner in their 2020 papers. So here you see that in equation 1 is the expression of the measure amplitude in frequency domain. But since the Riemann square amplitude in the time domain is equivalent to the Riemann square in the frequency domain, we can use the amplitude measure in frequency in time domain in this approach here to isolate the source extension term. So what makes the approach attractive is the fact that you can approximate the propagation term by piecewise linear function of the distance. So if you have several measurements from different aircraft at different stations, measured at different stations, equation 1 can be written in matrix form as an indication of equation 4. So where A is the area of measure amplitude, K is the matrix of coefficient, and M is the model parameter that we are trying to estimate. So we use a singular value decomposition technique to estimate the model parameters, and also we were able to estimate the 95% confidence interval for each of the model parameters. Next slide, please. So here I'm showing you the result of that regression. On the left, it's the distance term or the propagation term as function of distance. The dashed line in that plot is the model of a simple, you can see that in the plot, you have some slight dependencies of frequencies with the high frequency signal slightly more attenuated than lower frequency signal. On the right, I'm showing you the side term for each of the frequency bands we investigated. You can see that the pattern of side term is consistent among for the different frequency bands we investigated. And most of the stations are showing damping. And we think this is related to the fact that the stations are located in a basin area where you have sedimentary material near the surface. Next slide, please. Here on the left, I'm showing you the estimated source term as a function of magnitude. This is what we wanted, right? That you have the source term increase in magnitude. If you look carefully, you can see that the degree of scattering increase with increasing frequency. We think it's related to the fact that at higher frequency, you have probably a worsening of the quality of the waveform. On the right, I'm showing you for each frequency band investigated, the raw curve and the associated area under the curve. The area under the curve is a measure of the performance of the classifier. So you can see that the range of area under the curve range from 0.8 to 0.9, with the highest value associated with SG measured at frequency between 10 and 15 Hertz, to SG measure between 20 and 30 Hertz. Next slide, please. So we were able to investigate 4 classes of classifier, RG, SG, ML, MC, low frequency SG, high frequency SG, and PG SG. You have 2 extreme cases here. For RG, SG on the left, you have the area under the curve that is nearly 1, which indicate that for the population of event we investigated, this is an ideal classifier. On the other hand, for PGSG, The area under the curve is 0.57, which is only slightly better than a random classifier. We also estimated the likelihood of misclassification using the Malawi distance calculated as shown in the equation you see on the slide. For the best performing classifier, single classifier, we have a minimum likelihood of misclassification of 4.3%, which is very good. But we think that there's still room for improvement. Next slide, please. For that reason, what we did is that we tried to combine the single classifier into two or more, by combining two or more classifiers to improve the discrimination power. I will not go into the details of the approach here. What I will say is that we define the discriminant function I indicated in equation 5. For an event of interest with parameter x, the event is classified as mining blast if d of x is positive, and the event is classified as earthquake if d of x is negative, with d equals 0 representing the classification line. Next slide, please. So by doing so, this is the summary for when you combine two single classifiers. You see that we achieve an improvement in a likelihood of misclassification of 4.1. On the right, I'm showing you the 2D plot of the parameters. Next slide, please. And I would like to mention that the improvement here is relative to the best performing single classifier, which is RG to SG. So here, I'm showing the result when we try to combine three classifiers. And only when we combine low frequency SG to high frequency, and to high frequency SG, RG to SG, and ML minus MC, we have a slight improvement compared to the case where we combine two classifiers. For the other combination, either there is no improvement or there's even a worsening of the performance. Next slide, please.
Rico, if you could conclude, please. If you could conclude within a minute.
Yeah, yeah, this is my last slide. Okay. And yeah, I will leave you with the conclusion. Thank you very much.
We may have time for one short question. Okay, no questions. Thank you, Rico.
Thank you.
So I'd like to invite Fekadu for his talk, which is a comparison of REB with ISC. On second thought, I will tell you when it's like 3 minutes before the end so that you can also arrange your time, okay? Okay, thank you.
Okay, so please, could you bring Okay, thank you very much. My name is Fekadu Kebede. I'm from Addis Ababa University, Ethiopia. So the title of my talk is Quality Assessment of the Reviewed Event Bulletin through the comparison with the ISC Bulletin for the October 2007. No, for October 2020. Okay, the outline of my talk is as follows. First, objectives, then data selection, then comparison approach, comparison results, and the comparison of some outputs from earlier results, because I had been here, so I have done over several years this type of comparison. So I want to show you some of the stuff, if there is a status change. So the sample waveform data for matched and unmatched ISC events. That means for some of the events we at the CTBTO we could not locate them. And then finally, a comment and summary. Okay, the objectives of the study are follows: to assess if there are potential events missed by from the reviewed event bulletin from REB. That's one. Two, to assess if there is a change in current parameters estimates when compared to investigations made earlier using the similar approach and also using the same data, ICC and IDC. So, data selection and usage is performed as follows. Data from the International Seismological Center, ICC, is utilized. At that time when I was doing this work, I could not have access to the IDC because I went back, so I needed to have access to the IDC. So at that time I didn't get, so I was totally dependent on ICC database. And for the data, 1 month of data, that is in this case October 2020, was selected for comparison. Sorry. Close it. Okay. So then selection of the October's data was based on, because the data was the one which is available at that time, the latest data available at that time. So then the comparison approach. So the ICC bulletin contains all available event solutions from contributing agencies and also its own. All are on separate lines, so we can easily see which ones are associated or merged, which ones are not merged. Hence, common events are ready for grouping, and that allowed us to extract the merged information, the merged event information. So this is just for October 2020. The data on the left is from IDC, the 2,652, that is excluding the infrasound stations. There are about 39 infrasound stations because they are not included in the ICC bulletin, so there is no point for comparing them. And the one on the right-hand side is 3,431. These are ICC students. From the figures, it looks like as if there is no difference, but if you closely look at them, there are some slight differences. Okay. Geographic distribution of merged events. These are the merged events. I divided them into two, just in terms of the epicentral location difference. On the on the left-hand side, this is the map showing those events which location difference is less than about 1 degree. That means they are well located, both located very close to each other. And the one on the right is greater than 1 degree. It's one. So, and for those large epicentral location differences, I have just plotted them. This is for location difference greater than 5 degrees. This is a little bit large. So for 2020, October 2020, that is mainly only for 3 to 6 defining stations. They are small, relatively, according to IDC language, they are small events. So you can see there are some in Asia, South Asia, and also in Latin America and South America. And actually, for the following reason, I was a little bit perplexed. I wanted to go into see, and since I worked only for 1 month's data, I went back to 2007 and see if we can see also the same pattern. And as you can see here again, even though there are few, for October 2007, we had in South America and also in Southeast Asia, we have events with location difference greater than 5 degrees. And for the year 2007 also, they show the same thing. So from these areas. And this is this is just a graphical presentation of the location differences. The one to the left for all of them, for the 3 cases, is for location difference less than 0.5 degrees. They are very close to each other. That goes for October 2020 about 86 to 87%. And for the same range for October 2007, it is about 89%, and for October 2007, it is about 91%. So this shows just a little bit, there is a small difference. And this, no. Okay, so I have shown here from earlier years also, for 2003, before SCPT, it is only 78%. So that's in 2003. In 2004, 2005, a lot of stations came into the IDC. So the percentage increased. And in 2007, we have about 91%. And for October 2007, we have about 89%. For October 2020, we have about 86 to 87%. That means yes, there is a slight decrease. So otherwise, more or less, they have the statistics looks like the same. And this is the error-ellipse intersection. So here is actually what bothered me to go back to October 2007 or year 2007 to look at them. As you can see here on the right-hand side, on the left-hand side, the error-ellipse intersection, non-intersecting error-ellipse, the percentage is high. It goes up to 43%. And then I decided to work also on October 2007 to see if I can see, because of the data, the amount of data. So I worked on October 2007. It is not like that. And for the whole year, again, on the right-hand side, both of them, they show nearly about 15%. But for October 2020, it showed a little bit more. Then I decided to see a little bit more. And okay, this is just a slide from 2003. As you can see, from 2003, the non-intersecting is around 15, 18, and something like that. But when it comes to October 2020, it goes to 43%, so a little bit high. So I decided to look into it more. And this is for October 2020. These are two events, one from IC and the other one from IDC, which are merged events. So they are very close to each other. The epicentral difference is 0.09 degree, and yet they are not intersecting. The error-ellipse intersecting. And so again, I found another one. You can see, again, the error-ellipse for IDC is high, it's larger, but still they are not intersecting. So I wanted to look for the same range of distance difference, what is happening in 2007. What we can see is, in this case, the IDC error-ellipse is very large, so it goes and intersects with the ISCC, as you can see from the two. So in this case, for the October 2020, the IDC error-ellipse are little shrinking, they are smaller. So this may be due to the increase in the number of stations. Okay, so this is unmatched IDC events. That means which are not included in the ISCC bulletin, which are not located by the ISCC bulletin. As you can see, okay, these are maybe, most of them I could say, ISCC didn't get data, additional data to change the location of the IDC. Okay, so these are unmatched ISCC events. Okay, so there are, if you look at the index, you can see there are events without magnitude. These are very small events, maybe explosions, or for which ISCC didn't get any data to calculate magnitude. And there are 12 of them with magnitude. So these are in color, so you can see them. And on the right hand, I put them separately on the right-hand side. So mostly they are in Latin America, and one is in Europe. One in Europe is about 3. I think it's because of the station configuration. And this shows you those 12 events missed by the IDC, for which ISC just calculates the magnitude. Most of them are above 4. And as you can see on the right-hand side, I also looked at, okay, are they missed totally? Do IMS stations miss all these stations events or not? So I looked at the ISCC catalog, and they have used, the one on the yes, okay. So the one on the right-hand side, it it gives you the number of IMS stations used by the ISC. So up to 5, up to 6 event stations, IMS stations were used to locate these events, and yet maybe they are not automatically detected, or for some other reasons, or the phases are misused, or so they were not involved. So we could not find any event for these events, but and yet the ISC have already used some of the IMS stations. And these are sample waveform data. For example, this is for the first event, and from SCGJ you can see you can identify P and S, and yet maybe there is no detection on the station at the IDC, or it is missed, or I don't know. I have not closely looked into it because I don't have access to IRS. Okay, again for this another event, you have 2 stations. I got data for that. So I go to the conclusion. Summary and conclusion. Comparison of IDC and IC bulletins for October 2020 shows that the percentage of matching is still high, and the maximum percentage of average location difference for less than 1 degree or less than 0.5 degree observed for since 2003, including this study shows, varies from 78 to 91%. The percentage of non-intersecting error depths obtained in this study shows there is a high percentage, which may need further investigation. Okay, this actually I could say that this could be due to the increase in the number of IMS stations recently as compared to the year 2007. And there are matched ISC events with M greater than 4 and recorded at several stations. Up to 200 stations have recorded, and yet we don't have in our bulletin. Some events with large location differences or D greater than 5 degrees are observed to be located in a few regions like South Asia, such as Asia and South America. Okay, thank you very much.
Thank you, Fekadu. Any questions for Fekadu? Maybe I can make a question until.
Yes.
I was wondering, the matching of the events, you got it from the ISC bulletin itself, I'm guessing.
Yes.
What I want to ask is when you showed the unmatched events and the magnitude, which magnitude was this? Was this the REB magnitude, or was this?
They are already missed in the REB, so we cannot have.
If you can speak on the microphone, please.
Okay. Yeah. They are already missed by the IDC, so there is no magnitude from IDC. They are not in our bulletin. So those events are in the ISC bulletin, for which ISC got some additional stations and calculate the magnitude.
The reason why I'm asking is that you know that the magnitude of the RB is very much different than.
Yes, I know, by about 0.345, yes.
And
less, yes.
I'm not sure. Maybe someone from the IC could tell us if the magnitude is also used as a criterion for matching events.
No.
It's not.
No, it's not. It's just
location and time.
They are grouping. Sometimes the IC doesn't have any magnitude at all because they didn't have any additional data. But as long as there is an IDC magnitude, it is there. IDC has one line, so the solution is there.
Okay. Any more questions?
Okay.
Thank you very much, Fekadu.
Okay.
The next presentation would be from Selby, and it's enhancing signal detection at the IMS seismometer arrays.
Okay, we got the slides. Is there a controller? Ah. Okay.
There is no pointer.
Okay, thank you. Title of my talk today is Enhancing Signal Detection at IMS Seismometer Arrays. I'm going to have a few slides about a detection algorithm called the Generalized F detector that I've been working on for some time and has been slowly being trialed and tested by other people. But the main part of my talk really is going to be about my personal point of view on signal detection and how, if we use good signal and noise models, we can not only design better detectors, but in this world moving forward into machine learning and various competing detection algorithms, we can understand how these things might work and how they compare to each other. Okay, so I think I just said that. So the generalized F detector, and you can see some references there. It's essentially a weighted least squares beamformer coupled with a statistical test for detection based on a non-central F statistic. Well, what does all that mean? Basically, the idea with the F detector, as we wrote it, was that we have a model for the noise. So when you have an array, you have a specific model for the noise. The coloured figure there on the left, you can see is an example at the array ArcS in Norway. And you can see the correlation of the noise as a function of the sensor separation and the frequency. And by using that model of the noise, you can both enhance the detection capability, but also reduce the number of false detections. Now, an F detector by its very nature has a signal model, which is essentially what you might call the perfect signal, which is that the signals are identical at every channel on the array. And that compares with a traditional, what you might call an STA, LTA detector on a beam formed as an array, where probably you would say that there is no real signal or noise model except that signals are bigger than the noise. The panel on the right there with the four squares and circles is basically showing how the noise model is explaining the distribution of the detection statistic. So, or if you go the other way, how it's unexplaining it, I suppose. So the F detector, generalized F detector, has a particular noise model, but the signal model is a sort of an end member. It's the perfect signal model, which is probably not universally valid. So moving forward, there has been a test data set at the IDC on the link there. I'm aware that some people here in the room won't be able to get hold of that if they were interested. But there has been an ongoing look at that test data set. We had previous testing going back many years. In particular here, the figure on the right is by one of my colleagues, Stuart Nippress, looking at the performance of both the generalized F detector and the current IDC signal detector, which is DFX, versus the LEB. We do see one or two stations where the generalized F detector doesn't perform as well, but I think we understand why that is. For example, at the array TORD, it was going under, I think, a repairs or maintenance or an upgrade, I think, during that period. So not all the channels were available. And I think one of the things to take away from this figure is that, generally speaking, the generalized F detector does pretty good compared to the LEB. Some arrays not as well as DFX. What we should point out here, of course, is that because we have a good noise model for the generalized F detector, we very greatly reduce the number of what you might call false detections, or detections that aren't ultimately associated with events. But because we have this perfect noise model for the generalized F detector, it does mean that sometimes we miss signals that DFX might detect. Okay. One of the things we found with this test data set is part of the pipeline at the IDC for signal processing. We have a detector in DFX, but then there is the FK analysis. For those of you who aren't familiar, the FK analysis at arrays is looking at refining the azimuth and slowness of the arrival at the array. The left-hand column on the figures there shows the azimuth and slowness as reported by the generalized F detector, and on the right by the DFX FK process. And for a lot of the arrays, for example, S-Thermio at the top, the results are very comparable. At the bottom at ArcS, again, what we see there is that the DFX FK processing is basically going back and measuring the noise again. And what's happening here, I think, is that the noise model that the generalized F detector uses is not known about by the FK processing in DFX. So basically, it's just going back and measuring the noise as, because it's not understanding that the noise has this correlation structure that the generalized F detector is using. So having run through very briefly some things about the generalized F detector, I just wanted to go really now and talk a bit more about the philosophy of signal detection in general. So we have this IMS network, and of course the defining, as a seismologist I would say this, the defining characteristic of the International Monitoring System is the seismometer arrays. It's the thing that makes it different from the open source network of seismometers around the world. But the design of the arrays is very different for all sorts of historical and logistical reasons. So you go from a very small sort of 1 kilometer aperture array, such as the one at Spitsbergen, to a much larger aperture array at Norsa in Norway, which is pushing 50 kilometers or more aperture. And also there's different numbers of elements, and also the signal and noise characteristics are very different. And I don't think we've really made the effort to understand those signal and noise characteristics at all the arrays. And I'm not going to show you here, I'm just going to show you here some examples of the kind of things that you might look to measure. Okay, just as a slight aside, before we get onto that, the thing to talk about here is beam sets, and I don't know what happened there, but we've come back. So traditional array detectors, so I'm thinking both the existing DFX detector at the IDC and the generalized F detector use what you might call a beam set, which is a predefined grid of azimuths and slownesses on which to look for signals. So you form a beam, and then you see if there's whatever your detection statistic is, whether it passes a threshold. These beam sets, as used by the IDC, vary for all the stations. Some of them, no doubt, for good reasons, in that there's been a lot of work that's gone into designing them. For example, the one at Norsa there in the top right. Some, I think, are sort of more default, like the McCanchi one top left, and then others for historical reasons I don't know, like Yellowknife and Estomia. So they cover the slowness space in very different ways. They're very different. I guess my point about this is that these beam sets, if you're going to use a detector that uses these predefined beam sets, these should be based on the signal and noise characteristics as it applies to those particular arrays. Because every detection beam that you use is a signal hypothesis, and you need to take into account the signal and noise model and their likely uncertainties when detecting. One of the things that directly comes from that is if you look at the regional local signal slownesses, so we're talking about the phases such as PN, PG, SN, and LG. In these histograms here, the green histograms are showing you the distribution or the frequency distribution of those arrivals in the REB for a couple of years, 2021, 2022, as a function of slowness. And then the pink vertical dashed lines are showing you the slownesses of the beams in the detection beam sets, as I showed you in the previous slide. What you see is, of course, is that if you go through the bulletin and complete these histograms, you see that often there are no beams for the slownesses relating to the phase in question. So if you look at the top right, for the example there, LG at YKAA, the slowness is 0.2, well, the maximum there is, I don't know, 0.27. Obviously, if we went back to the previous slide, we can see that the maximum slowness in the detection beam set is 0.1. So it seems to me to be reasonable that if you want to find more LGs at Yellowknife, you should probably have beams for LG. Another thing that can happen, of course, is that we assume, well, many detectors, not all, will assume a plane wave crossing the array, and there's many reasons why that might not be the case. For example, geological variations. So the figures in the top right there in the yellow, we can see that the actual plane wave assumption may break down and the arrival time may vary across the array. There's also things like topographic variations. So the bottom left, the histogram, is showing you the standard deviation of the elevation of the elements in each array. And there are a few arrays in the IMS which have large topographic variations, and it would be very interesting to look at that to see what effect that has on signal detection. But also there's things like clock errors. A long time ago, back in I think 2012, there was an issue with leap seconds at the TORD array in Niger. So the plot there shows that Some of the elements had 1 second errors, some had 2 second errors, and it was all relating to how the firmware and the digitizers coped with the leap second. Also, as well as arrival time variations, you can get amplitude variations. So this is a signal at the Khatib array, Kazakhstan, P wave, 1 to 4 hertz. And you can see that even though it's a very simple signal, there's large variations in amplitude across the array, with 2 or 3 of the elements appearing not to see the signal, even though the noise is the same amplitude. One thing we have to be very careful about, though, when trying to model those kind of things, is we need to think about sensor calibrations, and also making sure that the signal and noise are varying by different amounts, because we don't want to just basically get a site amplification effect. We want to compare the signal and the noise. I spoke a bit about noise models. I'll show you again the figure from the previous slide. One of the things I wanted to say here really was that although there's been work done looking at the sort of typical signals that arrive at arrays, I don't think we fully understand the noise correlation structure. Even the array in the UK, Estomir, on the right here, you see all the channels. This is at low frequency, 0.1 to 0.3 hertz. The noise is very similar, but not quite exactly the same, and it's actually quite difficult to predict that noise, even though it does look very predictable. So again, I think increased understanding of noise models, noise correlation, noise power spectra at the arrays would improve our signals detection capability. And similarly with signals, some arrays are, the signals like we saw at Khatib are very similar across the array. Other arrays, such as the MJR array in Japan, the signals vary a lot. Whether that variation is predictable or not, I don't know. Perhaps there has been some work done on that. If anybody knows, please let me know. But again, understanding that variation would enhance our ability to detect signals at that array. Okay, thanks. Another thing that happens already in the IDC processing is that sometimes at some arrays, not all channels are used for beamforming at certain frequencies and at certain slownesses. The figure here in green at the top here is showing which elements in the array ArcS, again in Norway, are used on the left for around 2 hertz and on the right around 4 hertz. So you can see that different elements in the array are used differently depending on the frequency. And just as an example how that relates to a noise model, we can see at the bottom in grey are the weights that come out of the generalized F detector for that same array for the same frequencies. So those are similar but not quite the same as in the current processing. But this only exists for a few stations in the IDC processing at the moment, and perhaps there could be work done to see if this could be extended to other arrays. And then I think, as I mentioned at the start, if we understand our signal and noise models, we can compare different detection statistics or different detection algorithms. The figures here are actually from a poster at the SnT2023, but I brought them up here just because they sort of fit into the theme I was talking about. I'm comparing their essentially beam power and the F statistic for 2 arrays, MKAR and TORD. And what you see there is that relationship between those 2 statistics is different for the 2 arrays. And this is both because of the difference in the array design and also because of the difference in the signal and noise models. So if you understand your signal and noise models at different arrays, you can predict this sort of thing, and it helps you either combine statistics or look for outliers where one statistic is being met and the other isn't, for example. And we're nearly finished. So this slide was just really, I call it network detection, but this is really sort of the transition between what you would call signal detection and association. So you can talk about the characteristics of noise and signal models at a particular array, but then you can also talk about the characteristics of the Earth and how that affects detection. And as you go down this list here, it becomes more and more really about association rather than about detection. But I think in some sense, ultimately, we might end up in a system where we don't call detections at particular arrays. We just generate a continuous statistic as a function of azimuth, slowness, frequency, whatever else, and then we combine those all into a sort of event detection global network processing. And I think that might be the ultimate end game. Okay, so just to conclude, the IMS seismometer arrays have a variety of sizes and designs. Signal detection approaches should account for these. Improved signal and noise models tailored to specific arrays will enhance our capability to distinguish signal from noise, and the framework should allow detection statistics to be more usefully interpreted and compared. If we move forward to a system where we have multiple detection algorithms, and we want to know how to compare those and which arrays to deploy those on, understanding signal and noise models will allow us to do that. Global network approaches can use our knowledge of the Earth and seismicity to enhance detection, but we should take a great deal of care not to bias detection capability. What we don't want to do is basically tune our arrays to the point where they can no longer detect the things that we're looking for. Thank you.
Thank you, Nick. Unfortunately, we don't have time for any questions, so you can catch Neil after the session is over. I'd like to invite now Paul Richards to continue with.
So the person, I think it's Nick Aurora, giving the next talk can come up. I will take over as convener. Hello, Nick. The next paper on the current status of NetVisa toward the operational use for nuclear explosion monitoring is co-authored also by Megan Slinkard, Vera, Tamarit, Gaeta Aurora, Sharif Ali, Ronan Lebras, and Noriyuki Kushida. So Aurora, I think, is to give the paper, and I will give you some warning after 12 minutes, okay, and so that we would like to conclude and with a question or two at the end. Thank you.
Okay, thank you. All right, good evening, everyone. This work has mostly been done here at the IDC, and as part of as contractors, we were simply assisting in a role that we could. Mostly Vera, Noriyuki, Ronan, and Sharif have been doing, and others at IDC have been doing the analysis of NetVisa and helping it move it along into operations. So this is where we stand right now. I will just briefly go over some of the configurations that are being tested at IDC and some analyst work that was done, and where we stand and what needs to be done next. All right, so I guess probably not a good idea to go back into explaining what NetVisa is at this point. I think some of you already are familiar. Very briefly, it's a Bayesian model for what is called as a network processing by some people or associated by some people. It's basically based on a model of global scale seismology at a very coarse level, and that helps to interpret the data that the IDC produces in terms of the IMS data and then the DFX and other station processing data that goes after it. And this one takes it from there onwards to producing an event bulletin. So right now, the current configuration is that there's an existing software called Global Association, which is given to, which is used to produce the CEL3 bulletin. This is given to the analyst, and they use that to produce a bulletin, and they get the option to say scan, and which means get me additional events. Prior to 2018, the scan button meant that there's an existing scanner algorithm that was developed by other contractors here who it is based on a very simple heuristic of trying to match pairs of events, pairs of detections that could come from the same event. After 2018, the scanner button also includes results from the NetVisa bulletin that were not in GA or CEL3. Right? So it has to be a completely distinct set of events. And there's another talk, poster here by Ronan and others talking about the effect of adding NetVisa in the scanner. I think they have a poster. You should please look at that. I think they talk about how adding that has caused the REB events to increase by 4.3% or some number like that. And I think in this talk, we will talk about what it will look like when NetVisa is made operational. So the roles of GA and NetVisa would reverse. All right. So this is kind of the picturization of what I just talked about. cell 1, cell 2, cell 3, the different products of the IDC, cell 3 being the last automated product. That goes to the analyst, they scan it, produce, and they look at NetVisa, and A cell 3 is the alternate cell 3, which is being published. So currently, the alternate cell 3 is coming from NetVisa. And they produce what is called the LEB, from which the REB bulletin is derived. And so what we have been doing here at the IDC is running a pipeline where we kind of reversing that role of NetVisa and GA. A workstation has been provided so a lead analyst can go in and actually pretend that this is their actual operations and work on it. And we can then look at their results and get feedback from them. So when in the alternate configuration, when the lead analyst press scan, they get the results of GA that were not in NetVisa. So the roles are kind of inverted for the two bulletins. That's kind of what that's the alternate picture. So the GA bulletin is provides the A cell 3 bulletin in this version of events. All right. Okay, so this is available, and so before I get into talking about some of the analysis, just briefly talking about how we measure various bulletins. As we saw in the earlier talk, the LEB or REB bulletin is not complete. There's a lot of missing events that ISC finds. So we choose to avoid using words like real events, false events, missed events, and things like that, because we don't really know what they are. What we do instead is talk about overlap and inconsistency. This is a term invented by Mark Pryor, who's sitting there. So basically, overlap is how common the percentage of events that are common between two bulletins, a test bulletin and a reference bulletin. Inconsistency is the percentage of events in the test bulletin that are not found in the reference event. We choose to use these words to avoid putting any labels on them. And we have a weak criteria which just looks at the number of shared associations between them. All right, so with that out of the way, here is some results. As I said, we have been running this continuously at IDC. This is the results for some number of months here. What you can see in this picture is the blue line is the NetVisa overlap. It varies about 80% and goes down on certain days. GA is about 10-15% points below that. Inconsistency of the two bulletins is about 40-50% and kind of hovers very close to each other overall. And these results are pretty consistent to what a lot of offline testing has also shown, except now it's running as if it is almost in production. There. Okay. And so what we decided to do is get a lead analyst come in and actually do the series of steps that analyst would do when NetVisa would be in production. So again, analysts are a very precious resource here at IDC. So we could only get this analysis at this point for a single day. It was 4th of February, 2023. And they compared the two operations. On the left, we have the regular one, which is starting from GA. So GA found 155 events. NetVisa found 169 events on that day. The LEB was built with 110 events as in regular operations, and the one that was starting from NetVisa produced 125 events. And just to be clear, this 125 does not include any hydro or infrasound. That was left out. It was only a seismic only on the right column. And from those, REB is produced. As some of you know, REB is just a automated screening of events in LEB. I think of it like a high-pass filter, events that have very much stronger evidence or primary stations which are considered of higher quality. And then, so the number of events that were rejected is 72. This is rejected from the cell 3 bulletin, 72 versus 65, and 27 versus 21 number of scanned events. Again, in both configurations, the analysts are clicking on the scan button and pulling in further events. And this is kind of important because the events that are built by scanner are fairly expensive to build because as opposed to rejecting an event, which is like just mostly fewer clicks, scanning an event does take a lot more work, a lot more work by the analysts. And I think in some estimates of IDC that Mark did a while back, his estimate was a 10:1 ratio of overhead of rejecting, of creating a new event from scratch versus rejecting an event that the analyst doesn't like. So that those numbers are kind of relevant in that sense. Okay, so bottom line, 15% more are LEB events and about 10% more REB events are produced. There is a lot of discussion about the 169 versus 155 events, and Sheriff provided us a very interesting analysis of how that number could be, how that difference could be eliminated, which is subject for a future talk. But there's an ongoing work on getting that number down so that the total number of events on both the bulletins starting point is also identical. Okay, this is most of the work, and there were some minor issues that they found out which were fixed. There's some ongoing work of integration with RSTT, and this is fairly straightforward given that NetVisa uses the liblock library, which already has RSTT integrated into it. So that's done. There's a new confidence ellipse that has been developed for NetVisa. Again, I have a poster on that. But in this work, we chose not to do that, and I think our current plan for operational testing of NetVisa will not include the new confidence ellipse estimator to reduce the number of variables that we are considering for moving over. So it is currently, the plan for current operational testing is to keep the existing ellipse estimator. All right, and that's, so in conclusion, we have a real-time pipeline which pretends that NetVisa is in operations. Analysts can look at it, and they are looking at it, and we have plans for further analysis as requested by the waveform expert group. A single day of processing, we got 15% more LEB and 10% more REB for a single day. Ongoing work to reduce the total number of events so that they're the same between GA and NetVisa. All right, thank you.
So we welcome questions on this paper.
Neil in the back.
Yes, in the back, yes.
Thank you. When you did the test of the lead analyst, or I guess in general, do the LEBs produced by NetVisa and GA have the same rules, the same scores for building events? And also, did the analyst know which was which? Did you do a blind test?
Well, for the first question, the answer is yes. It was exactly the same setup, so there's no difference in LEB rules. And analyst was instructed to do exactly like as they would have done in their regular day jobs. But yes, it was not a blind test. They knew this is coming from NetVisa. It's pretty hard to do in general. The NetVisa bulletin looks very different if you, an analyst look at the many phases that GA does not associate that NetVisa associates. So it's very obvious just looking at the bulletin in a glance that is very different.
Thank you, Nima. And I think we will move on to the next paper on a new periodic Fisher scoring method for DOA estimation for seismic signals. I've got two different author lists. Khatib and Horin. Excuse me?
What? I didn't do anything.
So I have an author list. You can tell me what is wrong with it, but Khatib and Horin, Yale, Krasnia, Tirzach Rutenberg, perhaps?
No, I'm the
I'm
first
sorry.
one. I'm Malaak Khatib.
Yeah. So bad for a convener not to be able to see the screen. Yeah. Thank you. Please, try to get this right. So Malaak.
Thank you. Yes. Hi, thank you. My name is Malaak Khatib. I'm from Ben Gurion University. I'm going to present to you a new periodic iterative method for DOA estimation, and we're going to apply it on seismic arrays. My colleagues are Yocha and Yael from Seismic Nuclear Research Center and Tirza from Ben Gurion and Princeton University. So we have some motivation, background with the problem formulation and performance bounds, the proposed periodic Fisher scoring, the seismic measurement model we are using, and the simulations, and then conclusions. DOA estimation is a fundamental task in signal processing. It appears in many fields such as radar, wireless communication, speech enhancement, and many more. Our motivation here is to accurately estimate the direction of arrival to improve early warning sign and better assess seismic risk. DOA estimation sensor arrays, especially in seismic arrays, it's a fundamental periodic parameter estimation problem, and we want to use the periodic aspect of the problem to enhance the performance of DOA estimation. And we're going to implement the method on seismic azimuth estimation. I want to highlight that we are using the method on seismic arrays, but we can use any planar sensor array you want, acoustic, hydroacoustic, and many more. We published recently a paper. It was accepted for the Fusion Conference 2023, if you want. For problem formulation, we have the observation vector X. It's with probability density function parameterized by an unknown deterministic parameter theta in the range -pi to pi. Assuming parameter estimation, we have H, a periodic 2 pi periodic function with respect to theta, and V is the additive noise. Taking the special case where V is a complex Gaussian noise, we get that the observation vector is also a complex Gaussian vector with mean H theta and covariance matrix RV. In this work, we denote the estimator by theta hat. It's a function by the observation vectors. For performance measures, we can use the conventional cost functions such as the mean square error, but in periodic parameter estimation, if we were to take this case where the 2 points are actually very close on the circle, we will get very large error compared to if we were to take periodic cost functions. The error would be very small because on the circle they're very close points. So we are taking the mean cyclic error. It's for performance analysis. It's given right here. It's a cyclic approximation of the squared error. As you can see, there is a range where the two errors coincide, but we are more interested in the regions where there is a difference between the two errors to highlight the periodicity of the problem. The Kramer-Rao bound is a lower bound for any mean unbiased estimator, but as you can see in the right graph, it isn't a valid lower bound for the problem, so it's inappropriate to use it as a performance analysis. So instead, we are using the cyclic CRB, which has been shown to be a valid lower bound for the mean cyclic error and has been shown to coincide with the Kramer-Rao bound for very high SNRs. You can see here that it is a valid lower bound, whereas the CRB isn't a valid bound. So we're using the cyclic CRB for performance analysis. Estimation methods. The maximum likelihood estimator is very commonly used. It's a maximization of the likelihood function or the log likelihood function. In general, this maximization isn't always solved, which requires a grid search, or sometimes for accurately parameter estimations, we require a very dense grid search. So we propose using the iterative Fisher scoring method to converge to the maximum likelihood estimator. It's an adjustment of the Newton-Raphson method, which is given right here. Instead of taking the second derivative, we approximate it by using the mean second derivative, which is given by the Fisher information matrix. The Fisher scoring method is this update function right here. It uses the CRB for each update step. The Fisher scoring method is an iterative method. We use it instead of other iterative methods because it's computationally more efficient than other methods to converge to the maximum likelihood estimator. Again, this method doesn't view the problem on a circle like we want it to do. So as you can see here, it still doesn't look at the problem as a circle, it just looks at a problem as an estimation range. So we propose the periodic Fisher scoring method to solve a few Fisher scoring problems. One of them is the fact that the Fisher scoring method is dependent on the CRB for each update step, which isn't a valid bound for periodic parameter problems. So instead, we suggest just replacing it with the cyclic Kremer-Rowe bound, which is a valid lower bound. The second problem is the fact that we need the estimator to stay in the range -pi to pi for each update step, and we need the error to be computed along a circle. So we perform modulo 2pi for each iteration. This is the proposed Fisher scoring method. Now we apply it for a seismic measurements model. We take the following measurement model. It's a planar array composed of K sensors. We assume a narrow-bound far-field single source. Theta and alpha are the azimuth and incidence angle. V0 is the wave velocity. The steering vector here, as you can see, is a function periodic with respect to theta, so the measurement model we have here actually represents a periodic parameter estimation problem like we want. The simulations we will show are a result of synthetic data that was generated assuming the configuration of Mount Monroe seismic array. It's a small arbitrary seismic array located in northern Israel. It has 1 tridirectional sensor and 15 unidirectional sensors. This is the map of the sensor array, where the red circled one is actually the broadband station sensor in the sensor array. The noise covariance matrix has been shown, for example, in this work to be a non-diagonal matrix, which means that there are actually correlations between each sensor in the sensor array. But in seismic arrays, we usually assume a white noise, a spatially white noise, which means that the estimators actually use a misspecified model where they assume that the covariance matrix is a diagonal matrix. So the matrix on the right is the actual true colored noise covariance matrix that was generated by the data. The matrix on the left is the assumed white noise matrix the estimators use. Each pixel is a correlation between each sensor. So if you were to take the 6th row and the 8th column, it's the correlation between the 6th and 8th sensor. The left upper block on the right matrix is a tridirectional sensor correlation. Okay, so to summarize, the matrix on the left is the matrix that resulted from the measurements. The matrix on the left is the matrix that the estimators use. We generate the data using these incidence and wave velocity parameters and 100 time samples. These values we're taking from raw data. It's an average value of the incidence and wave velocity used. So these are results. Again, I said that we are interested to show the periodicity of the problem, so we took where the true DOA is at one edge of the range, where the starting point of the methods is at the other edge of the range. So if we were to look at it as a circle, these 2 points are very close together, but on the range they're at different edges. One thing to notice where the periodic Fisher scoring method attains the cyclic CRB for almost all of the SNRs, while the conventional Fisher scoring method has a much higher mean cyclic error and only attains the CRB for very high SNRs, which we expected. Another thing to notice is the fact that the cyclic CRB actually is a valid lower bound, and the CRB isn't a valid bound, it isn't an appropriate bound like we suspected. So to conclude, we have a new low complexity periodic Fisher scoring method. It's an adjustment of the Fisher scoring method to be used for periodic parameter estimation. In the simulation, we took the common misspecified estimation problem, where assuming the noise is white when actually it is a color noise. We show that the periodic Fisher scoring method has a much lower mean cyclic error compared to the conventional Fisher scoring method, and it attains the cyclic CRB. Future research, we want to extend the method for multi-parameter periodic parameter estimation for both periodic and non-periodic parameters. We want to analytically explore the influence of mismatches such as misplaced sensors or misvalued incidence or wave velocity. And we want to check the sensitivity of the methods for the wave velocity and the incidence angle. Thank you.
Thank you.
I'm going to be sharing a method for detecting and estimating timing errors at seismograph arrays. In summary, this method enabled us to detect some very small timing errors that were present at the Yellowknife seismic array between 2013 and 2020. The sites affected were apparently random, but most interestingly, the timing errors were quantized and only increased with time. The method I'm going to show you gives good temporal resolution and excellent accuracy. In this case, it enabled us to guess that the system was occasionally losing 5 samples. It permitted us to model the timing errors well enough that they could be corrected. Now, that's not always going to be the case. It depends what's causing the timing errors, but I'm getting ahead of things. We've come a long way since the days of solar observations being used for timing at seismograph stations. Interestingly, when a seismograph station was first established in Ottawa, where the NDC for Canada is based, over 100 years ago, the location was chosen right beside a solar observatory for just this reason. Of course, those days are long gone as atomic clocks took over and we stopped using shortwave broadcast timing signals. And if you're like me, when GPS came along, you thought, that's it, we're done. Many of you will already be familiar with the Yellowknife seismic array. Neil mentioned it in his presentation. It was built in 1962 with a 2-kilometer station spacing. The east-west line is called the red line, and the north-south line is called the blue line. One of the purposes of the upgrade in 2013 was to improve timing. From the beginning, the timing was handled centrally. Starting in the late 1980s, the central clock was GOES, or it might have been the early 90s. But later on, this was changed to GPS. The tricky thing about this was that the empirical timing corrections had to be applied to account for telemetry propagation delays. The 2013 upgrade introduced a GPS receiver at each site so that in theory the data could be perfectly time-stamped at the site. Late last year, we were alerted to a potential timing problem by John Vidali. At right, you can see traces from 2 of his repeater earthquakes in green and red, one from 2003 and the other from 2017. You can see how most of the stations line up well, but a few don't. He couldn't make any sense of the pattern of stations affected. It seemed pretty random. My first thought was that maybe something was interfering with the GPS antenna, getting a good view of the sky. It turned out that we weren't archiving our GPS state of health, so we couldn't tell. We are archiving it now. Still, there were some status files available, and they showed no issues, but they spanned less than a month. I looked into whether the temperature dependence of damping could be causing variable delays, but that could only explain delays less than about 10 milliseconds. So how do you verify timing accuracy in the field? This is a long-standing problem, and there is no simple solution. It's easy if you have a co-located sensor, but most stations don't have that. Some researchers have also recently started trying to use large repeating earthquakes, including Yangsong and Ringler. There, it's a very interesting read. But the catalog of repeaters is small enough that you don't get much temporal resolution, something like 1 estimate a month on average. So my idea was to see what I could do with the fact that an array gives us repeated recordings of non-repeating earthquakes. An obvious choice for estimating the relative timing between sites is cross-correlation, And Van de Kar and Crossan give us a way of turning those pairwise estimates into an estimate of the delay at each site under the constraint that the delays sum to 0. I upsampled the signals to 100 samples per second to give improved time resolution, and I've been trying a couple different methods of estimating and correcting the move out across the array. This method is nice because it additionally gives you estimates of the mean square residual time delay at each site, and this can be used for quality control so that you can keep strong results and throw away weak results. After playing with the configuration a bit, I settled on a rather wide 1 to 10 hertz bandpass filter and a plus or minus 5 second window centered on the nominal AK135 arrival time. You can see in this plot, the orange band is plus or minus 2 times the RMS residual, and it picks out a noisy channel and a dead channel nicely. So once I had this working well, I analyzed about 2,500 events since 2010 from a particular source region in the South Sandwich Islands. Here's an example of one of the events from when the old and new arrays were running simultaneously in 2013. All of the traces from the two sets of stations are slightly offset, and I was able to confirm the same 0.1 second offset that Wayne Edwards reported in his study about the upgrade from 2014. He attributed the timing error to the empirical transmission delay correction of the old system, and I think he was right, but this was only 4 months into the operation of the updated array. In fact, during the whole 9 months of overlap, there were no incidences of site-specific timing errors. So here's an example. Uh-oh. Can you advance it for me? It's not responding. Thanks. The next slide will show an example of a strong result from a few years later in 2017. This is one of the same events that John Vidali first reported to us. You can see when the signal to noise is good, the RMS residuals get really small, and furthermore, you can see the same stations that Vidali noted are delayed. I don't know if I have a laser pointer here. No, there isn't. But in the bottom left, the second from the bottom and the fourth from the bottom, you can see an offset. Next slide, please. Oh, actually, I went too soon, but that's fine. So based on results like that, I settled on a quality control requirement that the RMS residual be less than 30 milliseconds. So with that screening in place, you can plot the zero mean arrival times as a function of time, and a really interesting pattern emerges. The top panel is the red line from east to west, and the bottom panel is the blue line from south to north. The horizontal axis is time from 2010 to 2023, and the vertical axis is zero mean time delay estimates. You can already see that the spread of timing delays is increasing with time. By trial and error, I was able to find a station without obvious timing errors, so I tried referencing the delays to that site. And here's what you get when you reference the delays to B8. You can see that the timing errors increase with time, and two instances when the errors are reset back to zero in December 2015 or January 2016, and another around April 2020. We still haven't explained the first reset, but the second one lines up perfectly with the firmware upgrade. I'll come back to that in a bit. You can see that the time delays of the other stations are mostly constant with time, except for occasional jumps, and there are offsets across the array due to move out. I've been playing with a couple of different ways to correct that move out. I'm hoping that this will allow me, I'm working on fitting plane waves to the delays, and I'm hoping that this will allow me to remove the constraint that all the events be from the same source region. But first, I'm going to show you a cruder method of dealing with the move out. For this plot, all I've done is use a time period in early 2016 when the timing errors were all apparently close to zero to estimate the mean move out for events from this source zone. So you can see that the timing errors, now you can see it clearly that the timing errors are quantized. By picking out a time in early 2018 when the delays were constant, I was able to estimate the quantum of timing error to be 121 milliseconds. Right away, this struck me as being close to 5 samples at 40 samples per second, or 1/8 of a second. Another thing that becomes clear with the move-out correction is that there are a few episodes of non-quantized timing errors. In both cases, they're on the red light line, so the bottom panel. One is the blue markers, and the other one is the red markers. These might be your more garden variety issues with clocks losing lock with respect to GPS. Next slide, please. If we make histograms of the timing error, we now can pick out other stations that could have been used as references, B0 being R7 or R9. And if the timing is perfect, other than the quantized errors, we can estimate the accuracy of this method for estimating them as being better than 10 milliseconds, so less than a sample. I had some very helpful conversations with GURALP support, and they were able to confirm that for some versions of the firmware, there was an issue with the bus that sends data between the DSP and the CPU. Data is sent on that bus in packets of 5 samples, so that's your 125 milliseconds. Furthermore, once a packet is lost, and this happens very rarely, all subsequent data appears delayed by that same amount. The issue was apparently fixed by GURALP in May of 2012, but we failed to upgrade our firmware. So I know the range of problematic firmware versions, but I don't know what firmware version is in use where in the IMS. I do know where the same model of digitizer is deployed. You can see them circled in this plot. YKA is in red because it displayed a timing problem. Green are the other arrays I've checked so far and haven't shown a timing problem. And orange are the ones I haven't checked yet. So next slide. Very quickly, this is a result from ARCAS showing no significant timing errors, and I was able to use the events from the same source zone. Next slide. Here's Gares, and it's in the P-wave shadow of the South Sandwich Islands, so I had to use a source zone near Vanuatu. Still no significant timing errors. And ILAR doesn't have the same GURALP digitizer, but it was an array that John Vidali reported as having good timing, so I had to take a look. The timing is good, but here there's actually a bit more scatter in the results. Final slide. I've got a few more IMS arrays to check, and I'm working to tabulate and publish the quantized timing error with time. I'm also interested in trying to remove the constraint that events be in one source region. One problem here is that the method for estimating move-out delays must rely on some sort of outlier detection and not fit the plane wave to the outliers. This in turn means that the method will only work when there are enough stations unaffected to fit a plane wave. That means that at Yellowknife, this would have worked in the early days after the upgrade in 2015, but not at the end in 2019 when all but 4 stations were affected. Of course, this is probably fine because it shouldn't take us 7 years to detect and address a problem like this if we had the will and a way to detect it, which I think we have now. John Vidali has confirmed that with these timing corrections, he's getting consistent results before and after the upgrade. And I think it is likely that beamforming at PS09 has been impeded by these timing errors between 2014 and 2020. A couple of other things we learned: you gotta archive your GPS state of health, and you gotta keep your firmware up to date, and we need more methods to test timing in situ. Next slide. Thank you.
Thank you. I found that fascinating. As a strong proponent of precision seismology, especially in the context of studies of inner core rotation, it really matters. Questions are invited for the speaker.
So I did a little bit of a study on this with nodal deployments for kind of the on-site inspection aspects of it. Have you looked at possibly doing that, putting out nodals and comparing them and seeing what results you get from that?
I'm sure that would work, and you could deploy almost any kind of a sensor. Another type of sensor that would work and is really easy to deploy is an accelerometer. But the problem is the need for continuous monitoring in situ. And then even if you decide that you can't really solve it by just going and deploying a second sensor, because it could be affected by the same types of timing errors. So there really is a need. Here I seem to have come up with a solution for arrays and a way to do it in situ, but there's still a need for a standalone station for a way to detect timing errors without taking extra equipment to the site. But you're right, that would work and is an important method.
If you'll excuse a naive question from me, so to the extent that you find a plausible cause, and you had a list there of making sure that the firmware was corrected and that when you have packets that somehow coincide, 1 in 5, so, is there a way to go back and correct the archive of
The archival data, very good point. I'm sure you could.
Yeah.
And maybe that's what should be done. You know, it's an unusual situation that it's such a deterministic error, like that it's exactly lined up to a certain number of samples. So I think in this instance that might be the right thing to do. For now, it's easy enough to apply it after the fact.
So seismology, in my opinion, is a collection of all sorts of different subjects. And most people spend their career maybe working on 5% of all of seismology.
Yeah.
So in some areas, most notably the one that you mentioned with John Vidali and Song, in the core rotation, you need to study a 20-minute travel time and see how it can change at the level of 0.1 second over 10 years. And then you get a great scientific result.
Yeah,
Perhaps not so important in most of our own work here in monitoring for explosions and event locations. But the best we can do is perhaps yet still capable of improvement when you have found the underlying cause and removed it.
Yeah.
Any more questions for the speaker? So I think that concludes our session. What a range of different papers we have had. Thank you very much for all the speakers. Thank you for the people who made it work in the corner there. Thank you for the audience for your questions and attendance.